On your mark, ready, set, let's go. Trigonometry, bro, I know you know. I go psycho when I see a triangle. Just can't sit, gotta get tricky with it. That's it, 3 angles, 3 sides. T-R-I-G, all up in my eye. Soka, Toa, we'll tell you where to go. You just gotta know.
Communication Trig Part 1. What is a radian? Use a degree measure and radian measure of a circle to explain how you can derive conversion factors to convert between the two units of measure. So the first part of this question is asking, what is a radian? By definition, a radian is the measure of the angle, theta in this case, subtended at the center of a circle by an arc that has the same length as the radius of the circle. So basically what this means is that this arc length, this portion of the circle, is equal in length to the radius of the entire circle, and that this angle theta is opposite to this arc length, and the arc length is opposite to angle theta. And when all these conditions are met, it is said that theta is equal to 1 radian. The next part of this question is asking us to use a degree measure and radian measure of a circle to explain how we can derive the conversion factors. So first of all, the degree measure of a circle is 360 degrees. We know this from common knowledge. Now the radian measure of a circle is 2 pi rads. If you didn't know that the radian measure of a whole circle is 2 pi rads, we could easily derive it from the formula radians equals arc length over radius. So how do we do this? First of all, we set up our variables. So radians is unknown. Our arc length of an entire circle is equal to the circumference of the entire circle. They're the same thing. And the radius, in this case, we're going to leave it as r. So now if we fill in what we know into our formula, we get that radians equals 2 pi r over r. And now we can cross out the r's, and we're left with 2 pi. That's why there are 2 pi radians in a full circle. Now for our conversion factors. So first off, to convert radians to degrees, first we're going to set up both sides. So there's 2 pi radians in a circle, and there's also 360 degrees in a full circle. Now that we have this equation, we can divide both sides by 2 to get that pi radians equals 180 degrees. Then again, we can divide both sides by pi to get that 1 radian is equal to 180 degrees divided by pi. Therefore, to convert from radians to degrees, multiply by 180 divided by pi, since 1 radian can be expressed as 180 degrees divided by pi. So we can check this very easily by subbing in what we already know about a circle's measures, radian measures and degree measures. So a radian measure of a circle is 2 pi. We can times that by our conversion factor, and we're going to get 2 times 180 since the pi's will cancel out, and we'll be left with 360 degrees. Now, to convert the other way, degrees to radians, again we set up both sides. So 2 pi radian equals 360 degrees. We divide both sides by 2 again to get pi radians equals 180 degrees. And now we divide both sides by 180 degrees to get 1 degrees equal to pi over 180. This is our conversion factor. Therefore, to convert from degrees to radians, multiply by pi over 180 since 1 degree can be expressed as pi over 180. We can check this again by using 360 degrees, our degree measure of a circle, times by our conversion factor to get 360 pi over 180. And then we can simplify that to 2 pi. Or if we want, we can plug this number into our calculator to get 6.28 in decimal form. That's how you convert from degrees to radians and radians to degrees.
Knowledge Trig Part 1. Find the exact value of sine pi over 12. Since pi over 12 is not a special angle, we have to find 2 angles that add or subtract to pi over 12 that are special angles. 2 examples of this are 4 pi over 12 minus 3 pi over 12, which simplifies to pi over 3 minus pi over 4, which are both special angles, and 3 pi over 12 minus 2 pi over 12, which simplifies to pi over 4 minus pi over 6, which are also both special angles. Substituting this expression in for sine pi over 12, we get sine pi over 12 equals sine pi over 3 minus pi over 4. Now that we have it in the form sine x minus y we can use our compound angle formula sin x minus y equals sin x cos y minus cos x sin y. In this case, pi over 3 is x and pi over 4 is y. Using that formula, we get sin pi over 3 times cos pi over 4 subtract cos pi over 3 times sin pi over 4. Now that each term has a special angle in it, we can use our triangles to simplify it. Sin pi over 3 equals opposite over hypotenuse. Cos pi over 4 equals adjacent over hypotenuse. Cos pi over 3 equals adjacent over hypotenuse. And cos pi over 4 equals opposite over hypotenuse. Now we can combine these terms and these terms together by multiplying them. Root 3 times 1 is root 3, and 2 times root 2 is 2 root 2. Subtract 1 times 1 is 1, over 2 times root 2 is 2 root 2. Since both of the terms have the same base, we can combine them by subtracting them. We get root 3 minus 1 all over 2 root 2. The last step is to rationalize the denominator to get rid of root 2 in the denominator. To do so, we multiply the whole term by root 2 over root 2. Root 2 times root 3 is root 6. Root 2 times negative 1 is negative root 2. And root 2 times root 2 is 2. Multiplied by 2 is 4. We cannot simplify this any further, so the exact value of sin pi over 12 is root 6 minus root 2 over 4.
This is a knowledge question for trig part 1. The example here is to use the double angle formula cos 2x equals 1 minus 2 sine squared x to find the exact value of sin pi over 12. Step 1 is to let x equal pi over 12, which you then take and substitute into the equation, which will leave you with cos 2 times pi over 12 equals 1 minus 2 sine squared pi over 12. I've chosen to work with the left side for now because it seems to be easier to simplify down at this point. So for this, what I've done is expanded out cos 2 pi over 12 and then simplified it down to cos pi over 6. Now cos pi over 6 is a special angle, so you can use the special angle triangle here to find the exact value of cos pi over 6, which happens to be root 3 over 2. Now you take this value and you sub it into your equation. Since root 3 over 2 is an exact value and you can't simplify it any further, we then move on to the right side. On the right side, what you would want to do is to isolate sin pi over 12. In order to do that, you first have to move over the 1. So you subtract 1 from both sides. And because the 1 is not a fraction and root 3 over 2 is, you have to change the 1 into a fraction, which will leave you with root 3 over 2 minus 2 over 2. Now, once you've done so, it will leave you with root 3 minus 2 all over 2. And so you would then want to bring over the negative 2 from the right side, and to do so you must divide. So it then changes to root 3 minus 2 all over 2 divided by negative 2. Because it's a fraction, you have to invert and multiply. So you change the equation again to root 3 minus 2 over 2 times negative 1 over 2. And the bottom obviously gets multiplied to 4 here, and then the next step is to remove the squared from sine squared pi over 2, and in order to do that, you take the square root of both sides. Now here, because the 4 is actually able to be square rooted, you can change that into a 2. And leave the top half of the equation under the square root. I've also decided to flip the order of negative root 3 plus 2, since it's just easier to read as 2 minus root 3. Since the question is asking for the exact value of sine pi over 12, you have to consider its position. So in this case, sine pi over 12 is actually in quadrant 1. and so therefore it's positive, which leaves your answer having to be positive, and so your answer is root of 2 minus root 3 all over 2.
This is the application question for trigonometry part 1. The question is, given sine theta equals 7 over 25, where theta is greater than 0 but less than pi over 2, sketch the angle and state the 6 trig ratios, determine cos 2 theta, and determine cosecant 2 theta. So starting off with part A, I know that sine equals opposite over hypotenuse, so 7 is the opposite and 25 is the hypotenuse. So when I have to sketch it, the terminal arm has to be drawn in the first quadrant because theta is supposed to be between 0 and pi over 2. So 25 is your hypotenuse, 7 is your opposite, and your missing side is the adjacent side. And to figure that out, I use the Pythagorean theorem, which is c squared equals a squared plus b squared. And after calculating it, I found out that b equals positive or negative 24. In this case, it's positive 24 because it's on the right side of the axis. And next, determining the 6 trig ratios. You already have one trig ratio, which is sine equals 7 over 25. The second one is cosine equals 24 over 25. The third one is tangent equals 7 over 24. So those first 3 are called your primary trig ratios, and then the next 3 are your reciprocal trig ratios, which is cosecant equals 25 over 7, secant equals 25 over 24, and cotangent equals 24 over 7. Now moving on to part B, cos 2 theta can be written, it's a double angle, so it can be written in 3 different ways, but I chose 1 minus 2 sine squared theta because it's the only way that only has sine on the right side, and since sine was the initial angle given, I thought it would work best. So I sub in what my trig ratio was for sine, which was 7 over 25, into the brackets, and then I square everything in the bracket and then multiply by 2, and since it's being subtracted, one is being subtracted by a fraction, I have to find a common denominator, which I chose 625, and I end off with cos 2 theta equals 527 over 625. For part C, cosecant theta is a reciprocal of sine theta, so for now I ignored the 2 and just brought it over, so 1 over sine 2 theta. And sine 2 theta is also a double angle, but unlike cos 2 theta, it only has one way of being written, which is 2 sine theta multiplied by cos theta. So now I used my trig identities that I found earlier and plugged in the trig identity for sine and for cos, and then multiplied those together and then multiplied by 2, leaving me with 1 over 336 over 625. And since they're both being divided, I took the reciprocal of the second term and multiplied it by the first term, so 1 over 1 times 625 over 336, which gives me the final answer as cosecant 2 theta equals 625 over 336.
Thinking, trig part 1, proving the following identity. 2 cot 2x plus tan x equals cot x. We're going to start with the right side because it's simpler to get into terms of sine and cosine. Cot x is equal to cosine x over sine x. That's using the quotient identity. Now let's move to the left side. The left side, to start getting it to sine and cosine, we're going to make 2 cot 2x equal 2 over tan 2x, and that is using the reciprocal identity. And then tan x is going to become sine x over cosine x, and that's using the quotient identity. Next, we're going to want to break the tan 2x up. So it's going to become 2 over sine 2x over cos 2x, and that is using the quotient identity. Next, we're going to use the double angle formulas to break up sine 2x and cos 2x. Sine 2x is going to become 2 sine x cos x, and cos 2x is going to become cos squared x minus sine squared x. Next, we're going to inverse and multiply. So we take the 2 over 1 and multiply it it by that fraction. To multiply by that fraction, you're going to inverse it. So cos 2x minus sine 2x over 2 sine x cos x to become 2 cos squared x minus 2 sine squared x over 2 sine x cos x plus sine x cos x. Then we're going to make them their own fractions so we can cross things out. So it's become 2 cos squared x over 2 sine x cos x minus 2 sine squared x over 2 sine x cos x plus sine x over cos x. Now we're going to cross things out. So in the first one we can cross out the 2's, and on the bottom we can cross out a cos x and cross out the squared. On the second one we can cross out the 2's and the sine x on the bottom and the squared on the top. And we get left with cos x over sine x minus sine x over cos x plus sine x over cos x. Now we're going to cross out the sine x over cos x's because we're subtracting one and then adding one, so they cancel each other out. So we're left with cos x over sine x, therefore left side equals right side.